Welcome to the Explainer. Listen up, because if you are sitting for the Cambridge exams, and I'm talking about syllabus codes 0417, 0478, 0983, 0984, 2210, and especially the absolute heavyweight, the AS and A-level Computer Science 9618, you are in exactly the right place today. We are breaking down a topic that is quite literally a gatekeeper to those top-tier grade boundaries, constructing logic circuits from truth tables. Why are we zooming in on this specific area? Because the examiner reports are practically screaming at us. It appears in virtually every single examination series, and it's where dreams of an A-star either come to life or completely fall apart. Today, our core concept is simple. We're going to read the warning signs. We are going to avoid the common, devastating pitfalls that absolutely sink grades. Mastering the connection between truth tables, logic circuits, and algorithm evaluation is entirely non-negotiable if you want to succeed. So grab your notebook, eliminate your distractions, lock in your focus, and let's get started on mastering this critical syllabus area.
Okay, here is the exact roadmap we'll be using today to get you exam ready. We'll kick things off with the logic circuit challenge, then transition into core conceptual principles. After that, we're decoding the method mark strategy, exposing the top 3 examiner traps, and finally, we'll pull it all together into your final exam master plan.
Section 1, the logic circuit challenge. Let's dive right into the deep end.
Right, we really need to establish the high-stakes reality of the exam room here. I want you to imagine the clock is ticking down. You turn the page, and boom, there is a massive, daunting question, much like the infamous past paper code 9713. Constructing logic circuits isn't just about drawing nice little D-shapes for AND gates. It's a hardcore test of your algorithmic problem-solving skills, which brings up a question straight from the frustrated minds of the principal examiners. Why do students find evaluating algorithm efficiency so incredibly hard? Look, when you construct a logic circuit from a truth table, you're essentially building a physical algorithm. But when it comes to evaluating the efficiency of these systems, candidates just freeze up. They hit a wall. I want you to be totally honest with yourself right now. When you face a 6 or 8 mark evaluation question on a past paper, do you actually know exactly what the examiner is looking for? Or are you just throwing buzzwords at the page and hoping something sticks?
To really understand this, we need to look at 2 typical students. This perfectly illustrates the 2 most common ways candidates throw away easy marks. On the one side, we have Alex. Now, Alex is the kind of student who has practically memorized the entire textbook. But when faced with a logic circuit question, Alex completely overloads the page with raw computer science facts about AND, OR, and XOR gates, but provides absolutely zero analysis of the specific circuit in the actual question. The examiner's red pen just slashes through it. Then, on the other side, we have Sam. Sam is always watching the clock. Sam rushes the paper, completely missing the crucial command word requirements and completely ignoring the context of the scenario. The answer might be technically true, but it doesn't answer the prompt. Neither Alex nor Sam are using strategic analysis. Because of this, both of them are losing heavy marks, despite actually knowing the underlying theory. We are going to make sure you don't make their mistakes.
Moving on to Section 2, core conceptual principles. This is where we flip the script.
To avoid the traps that Alex and Sam fall into, you need a conceptual understanding that transfers seamlessly to completely unfamiliar contexts. Just consider this direct quote pulled straight from the Cambridge grading rooms. Principal examiner reports highlight that candidates referencing cross-topic connections achieve significantly higher marks. The 9618 syllabus, and really any Cambridge CS syllabus, isn't just a list of isolated facts. It demands evidence-based reasoning. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Seriously, do it, because making those cross-topic connections, like relating a logic circuit to processor architecture or data representation, is your golden ticket to the top grades.
So how do we actually make those connections? You need what we call systematic analysis. This is a framework drawing on precise definitions, causal relationships, and integration with other syllabus areas. And to execute this, top students use the PEEL framework. That stands for point, evidence, explanation, and link. Make your point about the logic gate, provide evidence from the given truth table, give an explanation of the Boolean logic behind it, and finally, link it back to the specific context of the question. That PEEL framework is the absolute foundation for algorithmic thinking. When you look at a complex truth table, you shouldn't just guess where the NAND gate goes. You need to systematically identify the causal relationships using PEEL. If input A and B are 1, what exactly causes the output to be 0? This framework is exactly how you evaluate alternatives efficiently and bag every single mark.
All right, Section 3, the method mark strategy. Let's talk about getting credit for your hard work. So the crucial point here is how you actually put this into practice on exam day. Examiners actively want to award you marks for your process, not just your final drawn circuit. These are called method marks. If you want to see those brutal red pen marks transform into beautiful green check marks on your paper, I want you to follow this exact 5-step computer science success blueprint for every single logic problem. First, identify the key elements from the truth table. Second, apply the relevant Boolean principles. Third, and pay attention because this is where the method marks live, execute your analysis with crystal clear working. Do not try to do it all in your head. You have to show the examiner your brainwaves. Fourth, verify your results by tracing the logic back through your circuit. And finally, present it in the exact format requested by the command word.
Executing that blueprint analysis requires really specific data interpretation skills. You need to be able to extract information rapidly from binary representations, perform the necessary Boolean calculations flawlessly, and draw evidence-based conclusions. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Remember, if your logic circuit is going to control something like a physical security system in the exam scenario, your conclusion absolutely needs to prove that it works under all given conditions.
Let's get into Section 4, Top 3 Examiner Traps. This is where we go hands-on.
Now that you have the methodology, we really need to expose the pitfalls. We're shifting into an interactive workshop mode right now. These are the most common grade-sinking errors pulled directly from the Cambridge grading rooms. Trap number 1, using the wrong formula or algorithm for the context. Trap number 2, forgetting to check boundary conditions and edge cases in your truth tables. And trap number 3, which is honestly the most fatal mistake I see, your answers are not specific to the given context in the question. If the exam question is about an automated greenhouse watering system, your explanation better be talking about moisture sensors and water valves, not just abstract inputs A, B, and X.
Let's do challenge number 1, the data scan. We have the trap on one side, ignoring context and edge cases, and the fix on the other, answers strictly specific to the given question context. I'm going to give you a mental 60-second visual countdown right now. I want you to mentally audit your own recent past paper attempts. Think about a complex data table you recently worked on. You have 60 seconds. Go. Are you scanning for the core trend? Are you actually looking at the edge cases, the 000 inputs, or the 111 inputs? Which side of the screen do your extended responses usually fall on? All right, time's ticking. If you're just writing generic definitions of an XOR gate without applying it to the specific data scan scenario, you are falling right into the trap. Time's up. You have to anchor your answers to the data.
Let's step it up to challenge number 2, find the flaw. I want you to imagine a flawed sample paragraph right in front of you. Ask yourself, which sentence in my extended response is losing the context mark? Read through your own typical paragraphs. If a sentence could apply to literally any logic circuit question on any exam paper ever printed, it is a wasted sentence. You will get 0 marks for it. Now, for challenge 3, speed writing. I'm putting 30 seconds on the clock. I want you to mentally draft one perfect Peel paragraph. Point, evidence, explanation, link, explaining why a NOR gate is used in a fire alarm circuit. 30 seconds, go. Think about it, state the point, give the binary evidence, explain the NOR logic, link it to the fire alarm triggering, and stop. If you couldn't do that clearly in 30 seconds, that is exactly where you need to focus your practice.
And this brilliantly illustrates our next major warning. Key terminology is a massive, massive stumbling block. The examiner reports explicitly state that candidates consistently confuse terms. The rule of thumb here is simple, but it saves grades. Always define your technical terms before you use them in your extended responses. Do not just assume the examiner knows what you mean by logic gate efficiency or combinational logic. Define the parameter quickly, in one sentence, and then apply it to the scenario. It shows the examiner you are in complete control of the computer science vocabulary.
We've reached Section 5, the final exam master plan. Let's bring it all home. We have covered the theory, the Peel framework, and the traps. Let's bring all these concepts together into a comprehensive answering system. We are talking about a system that guarantees top marks. When you are faced with a complex logic circuit problem that asks you to evaluate algorithm quality, you must use a critical analysis checklist. You need to consider time complexity, space complexity, rigorously test for edge cases, and analyze the overall effect on performance. Ask yourself, are there too many redundant gates in your circuit? Could it be simplified using Boolean algebra to improve performance or space? Run your solutions through this exact checklist every single time you do a past paper.
I want you to think of algorithmic thinking as a complete pie of practical application in the 9618 syllabus. It is split into 4 distinct, vital slices. First, you need step-by-step decomposition to break that massive truth table down into manageable parts. Second, you need appropriate data structure selection. Third, you need efficient code implementation, or in this case, highly efficient logic design. And finally, the 4th slice, rigorous testing. Listen to me. If you leave out the testing slice, if you don't manually trace your logic circuit back through the truth table to verify your outputs, your pie is fundamentally incomplete, and your final marks will absolutely reflect that missing piece.
To hit the absolute highest grade boundary, to get that A star, you have to satisfy what Cambridge specifically calls higher-order assessment objectives. This demands the evaluation of alternatives, the comparison of different approaches, and crucially, justified recommendations based entirely on evidence. You cannot just write Circuit A is better than Circuit B. That's what Sam does, and Sam loses marks. You have to explain that Circuit A uses fewer NAND gates, which reduces propagation delay and lowers manufacturing costs, thereby making it the undeniably superior recommendation for the given context. That is how you win. Let's quickly recap our final master plan system. Rule 1. Decode your command words carefully. Rule 2. Apply the Peel framework and systematic analysis. Rule 3. Manage your time matrix so you actually have minutes left to verify your logic circuits. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. AC Exams, your Cambridge success starts here.
So, leaving you with that final thought, what is your target grade for computer science and what is your absolute biggest challenge when it comes to evaluating algorithm efficiency or constructing logic circuits? Get down in the comments and let me know right now. Keep analyzing your circuits, keep practicing those past papers, and I will see you in the next explainer.